What are activation functions? A question that has plagued humanity from cavemen all the way to modern scientists. But you, as a student, should know what these functions actually are because you obviously want to use neural networks in your machine learning models. So, in part 3 of neural networks, we'll discuss what activation functions are and how they can set boundaries for outputs. So what are activation functions? Recall that inputs X have a weight W and a bias B. This was a while ago, and if you have short-term memory like me, you might not remember. But you can write that as X times W plus B. Remember the summation function where when we added weights and biases, the equation became Y equals X1 times weight 1 plus B plus X2 times weight 2 plus B. And we want to limit the output value of X times W plus B. Let's assign this equation a variable. Instead of Y, let's name it Z. So Z equals X times W plus B. And let's pass Z through an activation function. Activation function is literally what it sounds. It's a function that takes in some equation or input and puts out something. And activation functions limit the output value of any given input. Here, Z is a tensor input. So it's not just one variable, but imagine it to represent all of the input values in the neural network. All of those little circle neuron thingies that you saw in that image previously. Therefore, we refer to activation functions as f of z, since z is an input of this function. So now let's see the types of activation functions that we have. First is the step function. The graph is literally shaped like a step. So the step function only outputs a 0 or a 1, which makes it useful for classification. For example, if you want to classify fruit into apples or oranges, or if you want to classify a phone into Android or Apple, we all know that it's going to be Huawei. Anyways, the step function doesn't reflect small changes. That's why it's better to have a more dynamic function that actually reflects the minute changes in the function. Like, the step function can output a 0.8 to say that it's not exactly a 1, but it's a little slightly less than that. It will only output a 1. So that's where the sigmoid function comes in. This has the same lower and upper bound as the step function, but it's curved, which makes it more sensitive for small changes. The z in the formula is the same tensor variable we used before. Remember, z equals x times w plus b. Next is the hyperbolic tangent function, which is literally the same thing as the sigmoid function, except the lower and upper bounds are -1 to 1, where the sigmoid function was 0 to 1. There's practically no other difference as opposed to that. The next function is the ReLU function, one of the most common activation functions in neural networks. ReLU stands for rectified linear unit. It basically says that if the output is less than 0, we treat it as 0. If the output is greater than 0, then the output is just z, or the input we put. Remember the input. ReLU has really good performance, especially when dealing with vanishing gradient. Vanishing gradient is something you'll learn about in the next video on gradient descent. And other activation functions. These, I've only given you a small sample of the activation functions, probably the most common ones. But there are tons of other activation functions that if you want to check out, you can go to this Wikipedia link where it explains each one of them in great detail. So I'll see you guys in the next video where we'll talk about gradient descent and how that applies to neural networks. See you guys there.